and the voltage is 0. So it's between these 2 points that I draw a line, and the transistor is going to then operate in a circuit somewhere between these 2 points. So if it is fully closed, it'll be up here. If it is fully open, it'll be down here. Or if it is partially closed, then it's like this. Okay? So here, it could be at any one of these two, of any of these points. And these points are called Q points. The Q point is telling us the operating point. And the word Q stands for quiescent. So the word quiescent is used to identify the operating point of the transistor. What do we mean by operating point? In a given circuit, the transistor is going to, based on the value of V, R, this voltage and this resistance, that transistor may operate somewhere here, or here, or here, or here, or all the way at the cutoff point. Okay? When a transistor is used as an electronic switch, such as with our digital circuits, when we are talking about an AND gate, OR gate, NOT gate, all those chips, we have the transistor acting either on or off, open or closed. That is when it's either in the cutoff mode or in the saturation mode. When it is in an amplifier mode, then it is going to be somewhere between cutoff and saturation. Okay? So, that's my graph at the top of page 9. Let's look at the graph at the bottom of page 9. What the graph at the bottom of page 9 shows is all these other lines. And what are those other lines? The other lines represent the base current, which is saying that I have to have this base current in the first place to cause the collector current to flow. So what it's showing is I'm starting out with a small base current. So a small base current is shown like this, 100 microamps, let's say. So if I have 100 microamps, then my transistor is going to operate here. If I have 300 microamps, then the transistor might operate at this point on my graph. If I have 600 microamps, then the transistor is going to operate at this point on the graph. Okay? So depending on the amount of base current, I'm going to have the transistor operate close to cutoff or close to saturation. So can you appreciate the fact that with a large base current, if I put a large base current, does that mean that I've opened up my tap a lot? So opening up the tap a lot means there's a lot of base current flowing, which is causing a lot of collector current, and that means that I'm going close to saturation, and therefore the transistor is going to act more like a closed switch. That's, in a nutshell, how a transistor behaves. Okay? So that's my page 9. Now let's do an example, 2 examples, one with an NPN, the other one with a PNP, so that we understand more how the transistor behaves with some numbers, so we can associate some values to all this theory that we're learning. So, example 1, there are these equations on page 10, which we'll be using in doing our calculations. So as we do the calculations, we refer to those equations. So, let's start out on page 11 with example 1 and put some values in this figure. So let's go to the top of page 11. In an NPN transistor circuit, like the one we have here, VBB, 5 volts. VCC, 10 volts. RB, 100K. RC, 1K. And the last thing is HFE. This gain of the transistor, HFE, is given to be 150. Okay? That's something that you cannot determine. It is something that is inherent to the property of a transistor when it's manufactured. One day it may be 150, the next day it may be 175, another day it may be 200. That's just the way the transistors are. So in our circuit, HFE happens to be 150. So what are we going to do? Draw the graph of the, this is called the DC load line. This graph is called the DC load line. Okay, what does that mean? It's the graph between the two extreme points, saturation and cutoff. And then, based on that, calculate the current IB, the current IC, the current IE, and VCE. So once we determine IB, IC, IE, and VCE, then we know the point on the graph where the transistor is operating. Okay, so let's do that. So the first calculation is IB. IB, this current here. So what we're going to do is look at this left circuit in isolation. Do not look at the circuit on the right, just look at this circuit over here. And this current IB is V over R, Ohm's law, which happens to be, imagine the current to be the current in this resistor here, which is IB. So, the voltage on the left minus the voltage on the right divided by R. So the voltage on the left is VVB. The voltage on the right is this voltage here, from the base to the emitter. Okay? So that's VVE divided by RB. VBB is given to be 5 volts. VBE. BE happens to be the voltage from the base to the emitter through a PN junction. Here's P, here's N, PN junction, 0.7. You see where we get that 0.7? It is in a transistor between